Good morning. I'm happy to see that at least some of you managed to get up. The organizing committee is always smart enough to put some very interesting talks in the beginning of the day after the great dinner. So I assume that's why you managed to come. We got a great morning ahead of us. Unfortunately, the first speaker was not able to attend, but Arzu has promised to give her presentation instead. You all seen the slides now. The only thing I need to tell you is that the buses are leaving from the plenary hall, not from down here. And remember, there's no lunch built in today. Okay? Thank you.
Okay, thanks. Is this thing on at all?
Yes.
Hello? Oh, okay. Okay, good morning. I'll have to find my presentation first. That's okay. There you go. Which one?
Control plus L.
Okay. Okay. Okay, well, good morning. Where's the first slide? There you go. So Julianne couldn't make it. She's she's a student at Makerere University in Uganda, and she has a how do you call it? A scholarship to do her PhD in Holland. So half the time she spends in Uganda, half the time in Holland. And this time the situation with her visa didn't work out, and she couldn't make it. So also I haven't been in email contact with her for a long time because the email had broken down at her university. So what I have is a fairly rudimentary presentation, and also not quite complete, I'm afraid. So bear with me. I'm not completely sure what she was intending to tell at all points. So she did some simulations to mimic evil BI traffic across Europe to the Netherlands. Well, this is the overview of what she was planning to talk about. First of all, the little picture that we show all over with telescopes across Europe. Actually, there's also a telescope in the United States over there, which we have used at times. There are a few telescopes in the UK. There's one in Sweden, one in Torun in Poland. There's the Westerbork radio telescope and one in Medicina near Bologna in Italy. So we link these telescopes over the public networks, through the national NRENs, the NRENs, and over Géant. We've been doing this for a few years, first as an experiment, now we're doing it as a real project, trying to make this into a production VLBI service, connecting these radio telescopes to the correlator in Dwingelo in the Netherlands. So the typical round trip times of these connections are, well, from Westerbork, which is in the Netherlands, it's basically nothing, of course, and it goes from 10 to maybe 30 milliseconds inside Europe. Yeah, a little picture of so the tests were done. This was a situation in Dwingelo as it was. Actually, it's changed completely. What you see over there are, well, don't have a pointer. Those little boxes are the recording units that we have or the playback units rather, that we have in Dwingelo. Okay, there's another one again. So these little things, and this is the equipment in Amsterdam at SurfNet. And basically what we had, the situation was that there was a switch in Amsterdam and we had like patch cables of 200 kilometers and our units were connected to that switch. It's completely changed, as I said. Right now we have our own router in Dwingelo. So all the links that we were using were 1 gigabit per second. Okay, what was this about? So, what? I'm slightly wondering what she was. Yeah, so you can use different models, obviously. I must say I've forgotten what the general TCP/IP wide area traffic model was. The FTP, the SMTP models. So you try to find out how things like the timing of packets, the sizes of the windows, the congestion window, the receive window, all these things will affect the speed of the connection. It has proven much harder than we thought in the beginning to fill the links actually with single streams of data. I mean, you think it's easy, you stick in a 1 gigabit equipment and you have a gigabit, but you don't, as a rule. So there's some possibilities to trace the raw data. You can use, well, this is basically, of course, number one is like Web 100 tools. Specialized software and hardware, that's another possibility, it's proprietary stuff. And you can use, for instance, TCP dump. This is what she has been doing, actually, using TCP dump. She also tried to work with the Web 100 tools at some point, but and there's several possibilities of modeling the data flow, and what she has been using is the NS2, Network Simulation 2. So these are some data flow packet interval. Yeah. So what she shows over here is, there's a model also already over here, where she changes the packet interval. She found out of a packet interval that would easily sustain 512, which was the speed that we mostly work at, 512 megabit per second. And this is kind of a sanity check to see if you space them bigger, see what the simulation is doing. And well, it behaves as you would expect, for 3 different round trip times. In this, there's a variation of the data flow receiver buffer, which is actually done by changing the congestion window of the sender, because that's the only thing the simulation program can do. And here you again see behavior which seems to fit your expectations fairly well. For short round trip times, you get to the 512 megabit per second much faster than for the longer round trip times. Over here she started introducing background traffic, modeled as a Gaussian, which we can agree about or not. There are some studies that say you can model all the background TCP traffic on these links as a Gaussian. Actually, you can do these simulations also with many separate flows, small flows, big flows, but it makes the computation incredibly expensive and takes days just to calculate a few models. So what you see over here, that again, that the longest round trip time is affected first and most badly, which again you would expect. So. Okay. So she makes a little model of the throughput, which I think is mostly empirical. Just defining these as the throughput, packet size times 8, which is something she found empirically by as an ideal packet size to sustain 512 megabit per second. The maximum congestion window size, and then the EVLBI throughput can be written like that. And she finds that these 0.95 of the capacity of the link minus the background average, that the rate will follow this behavior more or less. Okay, so again, she has been doing research before also on real data flows, and what she found at that time was that the receiver hardware was really limiting the throughput of the flow. Of course, excessive background traffic is not one of our biggest problems mostly, but it can be quite bad. A lot of our links are nowadays completely reserved light path. So, and also she found that in real life, not in this, that the distances between the packets would get very big. It would behave quite bursty at times. So this, of course, can have a negative effect on the transfer. Well, then there's a little bit of the work that has to follow this. Yeah, I'm afraid that's it. How long did I do? Oh, 10 minutes. That's it.
I think we'll dare taking questions, even though you you cannot be expected to answer anything. Questions? I have one link to your presentation on Monday.
Ah, okay, sure.
Well, at that point you said everything is noise at the time it's actually transmitted at the network in your place. You still don't know if it's data or if it's noise.
No, it is data, but what you record, I mean, what you get from your receiver, from your telescope, is broadband Gaussian noise.
Exactly.
So you only can get the signal out by the correlation.
So I was wondering, are you sensitive to data loss in the network?
Yeah, of course, but it doesn't really matter very much.
So that's what I was thinking. Could you go to a UDP model and ignore all these buffer problems instead?
We tried, but the hardware doesn't like it very much because the whole system is built on receiving timed packets. So it gets packets with time codes. You start missing time codes and the system gets upset. It tries to... The whole correlate is built in such a way that you'll synchronize the data streams to an accuracy of better than a millionth of a second. So if it starts receiving holes in the data, so you would have to make an UDP in which you insert fake packets, basically. Which can be done. We're working on that also.
Okay. Always the problem with time. Anything else? Okay, thank you very much for being so brave to actually come.
Oh, you're welcome.
Hello. So I will present how we designed and deployed the firewall that will protect the LHC and the LCG. So I will give you a reason for the upgrade. What were the requirements, the hardware architecture, the software that managed all the system, and some experiences that we learned. So, just an introduction, what is the LHC? The LHC is a machine that will be used to study the secret of the matter. So, it's a big accelerator where the protons will be accelerated and made them crash together inside 4 detectors that you see on the bottom. So, these 4 big places. These detectors will produce a lot of data, so there will be 40 million collisions between protons per second, but only a few hundreds of them will be kept per second. Every collision will generate 3 or 4 megabytes of data, and this data has to be transferred to a computer center that will elaborate them. So we calculate that in 1 year, the 4 experiments will generate 10 petabytes of data, and all this data need 100,000 of the today's best CPU to be calculated. So how we will mangle all this data? We will use a computing grid. So on the top, you see all the application that the physicist will use. This application will run over a middleware of application that will, the real grid, that will, the management software of the grid. So this middleware layer will manage all the resources available, so storage, CPU, servers. But all these resources have to be connected by a network. So the model for the calculation is that there is a tier 0 center that is a CERN, the accelerator, that will produce the data and will do a long-term storage on tapes. The data will be distributed to the tier 1 centers. There are 11 computer centers that are directly connected to CERN with a 10 gig link, each one. And they will do the storage on disk, and also they will do some analysis. And then there will be another layer of computer centers, the tier 2, that will do final analysis and also give access to the end users. So how we build the network at CERN? So we have two backbones in practice. So the old one, that is a campus network where all the users and the servers are connected. Then for the LCG, for the tier 0, we'll build a new backbone here that you see is direct. Oops, sorry. Oops, it's wrong direction. Sorry. Yeah. That you see is directly connected to the tier 1 centers. This is LCOPN that is used only for the traffic between the tier 0 and the tier 1s. So it's a dedicated network, private. PN means private network. And to this backbone, there are all the storage and the CPUs at CERN, and also the experiments are directly connected here. The general connection, anyway, is made in this direction. So we have an external network that is connected to the internet. Today it's at 20 gig per second. And also the tier 2 centers are connected on the back. So the firewall I'm going to talk about is this one, the one that protects, in practice, CERN from all the traffic, generic traffic coming from the internet. It's not this one. This one is, due to the speed of the data, cannot be implemented with a stateful firewall, so we only use ACLs, stateless ACLs on the routers, on the bounder. So I'm going to talk about this firewall. That anyway, it will have a 20 gig connection. So what were the requirements? The CERN is not a bank, so we have to allow easy sharing of all the data, and we need to allow the users to share what they have. But still, we have to guarantee protection and also security. Another challenge was we need a high throughput to the network because of the data we will produce. And also for this project of the firewall, we had a finite budget that was also a challenge because we couldn't buy the best stuff on the market because they were too expensive. For the hardware, the requirement were that we need 2 gigabits for stateful inspection for all the generic traffic not identified. We wanted at least 20 gig traffics for high-speed data transfer, especially for traffic to the tier 2. Also, we wanted a fully redundant system and a flexible system to add security features when they will be needed. The requirement for the security was to be, since we have every machine has a public IP address at CERN, so every machine can be a server. So we wanted a system that was able to control every single IP address and also want to inspect all the traffic. That was not well defined. So this is a picture of the architecture that we designed in the beginning. So I will talk of this part because this is the backup path that should be identical. So we wanted an outside driving router that could decide where to send the traffic. For instance, the generic traffic should be sent to the stateful firewall. The high-speed traffic would have been sent to an high-speed bypass. And other traffic could be sent to IDS or to a throttle path. And the same inside. And then we also wanted a box that generated flow information. The system was quite complex, so it required a software framework that could manage it. And we developed a software that should have been integrated with the existing NMS that we had, and also with all the information we have in our database. And also we wanted it hardware independent, architecture independent, in order to reuse with different vendors, or also to use with other firewalls that we could have inside CERN. So this is the architecture Our firewall is the one in this yellow-orange area. These two are the external routers at CERN. These two are the internal backbone routers. So the main path is this one. We shrink the function of the external and internal driving router in one box. This allowed us to save a lot of money because this is a box with several 10 gig interfaces, so the cost was quite high if we had to have it double. And the firewall is connected with two links to the same routers. So now we will see how the traffic flows. And then this is the backup path. And these two send the traffic, mirrored traffic to another box that collect them and send to IDSs. So how the traffic flows from the internet, it arrives, the normal traffic is the blue line. So it comes to this driving router, let's call it like this, and it sends it to the stateful firewall, then it comes back and it's sent to the backbone. For the large volume data transfer, so traffic that is well defined, we know the source and destination IP address, so we trust it. We skip the firewall that is the slowest box of the chain, and we send it directly inside. How the routing is made. So we use two instances of OSPF, one in the external network and one in the internal network. As you see, the two driving routers are in the instance of the internal campus. And these two that are the backbone routers generate a default route for the rest of the campus. So these two collect all the traffic for all the campus. And then they send to one or the two using the route that comes from BGP. So we use an IBGP from the between the external backbone routers and the internal ones. So you see with the red lights a full mesh of IBGP peerings that goes this way, and another full mesh of IBGP peerings. So that goes to the backup path. The path is chosen using the local preference, so there is a better local preference on the primary path. The reason that we need two full meshes because when one of the firewall breaks, we didn't want that the peerings swap to the other one because we wanted to be sure to know where the traffic was flowing. So when, for instance, this firewall breaks, all these four peerings breaks. And we needed the double full mesh because for IBGP is a requirement to have this full mesh in any case, otherwise some routes will be lost with the other peerings. So these two routers generate a default route for the two inside. So they send a default route to these two. And these two announce the public prefixes that serves as, that is then forward sent again to the internet. How we achieve this of having the peerings on one path and another one is using static routes. So this router has a static route for the loopbacks, one of the internal routers in this direction. And this router has a static route for the loopbacks, one of the external routers in this direction towards the firewall. So in this way, we know for sure where the peerings are passing, and if something breaks, we know that the path is break. In this way, we also force the peering to go via the firewall, and this is used because if the firewall breaks, then we are sure that the traffic doesn't go directly to the external network. We also use a lot of policy-based routing because, as you can imagine, this traffic, the fact that we connect the firewall to a single router would create confusion here if we use only normal routing. So we had to force the traffic to follow some direction based on the source and destination addresses. So with the red arrows, you see where the policy routing is applied. It means that all the traffic, this red here, for instance, means that all the traffic coming from the internal network is sent either to the firewall, or if it matches a certain source and destination, is sent directly outside. Then all the traffic that comes out from the firewall in this external link, it's sent outside. Then we have all the traffic that match the same rule of this one. So all the well-defined traffic is sent inside using the normal routing, because this box, as you remember, is in the OSPF clouds as the internal network, so knows how to reach the inside destination. All the rest of the traffic that is not the well-defined one is sent to the firewall. Then when it comes out from the firewall, it's sent again inside using the normal routing, so it's a blue line. The management framework. We wanted something that was architecture independent, so we tried to design a model that could be adopted to any kind of firewall or filtering point. So we thought of a concept of gate. The gate is a set of routers, firewalls, stateful firewall, switches, any device that can apply an access list or a policy-based routing, or can do policy-based routing. And the gate is something that connects two domains. You see, we defined the domain left and right. We didn't define protected and unprotected, or inside or outside, because in fact the gate should be able to do protection in both directions. So we tried to keep it generic. But in the end, we had to put a distinction between the two, so we called them left and right, because we need to know where this, when we define, we will see later, when we define a rule with in the access list, we need to know where the source and the destination address are to allow the software to generate the correct access list. Then we have the concept of interface filter, that is the definition of an access list that give the direction of the default action we will see, and also it is applied to a physical interface of a box. And this interface filter can exist multiple for a gate, and can be applied to any interface of the gate. So we can have multiple interface filters. The interface filter is then links to several filters. Filters are a set of rules. So the filters can be used in different interface filters. So we can build a different generic filter that can be used in different gates or different interfaces. This is the schema of the database we used. So we have all the elements I mentioned, the gate, interface filter, the interface filter linked to the gate and to the device, so to the interface, and also links to one or more filter, and then the rule belongs to a filter. This is the framework that we built. It's built around our network database, something that we already had with information about the devices, the IP addresses. So we built an application that we call CSDB Web, that is the tool for expert user, for the network engineers, to build the gate and define all the interface filter and the filters. Then also we developed an interface for the end users. The end users can go to a web page and request an opening to the firewall. All the information are stored in this network database. And then we have a software, the configuration manager, that retrieve all the information and then create the final configuration and apply them to the real devices. We'll see now quickly all the different softwares. So this is the web interface used for the administration. It's written in Java. And this is main screen. So here we can define the gate with a generic name. We define here the two domains are connected. For instance, this is the internet, and GPN is general purpose network, the campus network. Here there are the list of devices. So these two should be one is the router and one is the firewall. And then you have all the interface filter. So we have an access list. Sorry, I had to cancel the names for security. The security officer asked me to erase any information that could be sensitive. And so we have all the interface filter. Here you should see the name of the interface of a device. And also the type, that can be a normal ACL, so filtering ACL, or a PBR, that is policy-based routing rule. This is the definition of the interface filter. So we have the name of the gate. The important information are this direction and the facing domain here. So these two give the direction of where the interface, how the access list is applied, and the domain where it's facing. These two information allow the configuration manager to build the correct access list. Here the interface where it is applied, and also the status of the access list, because we can disable the interface in case of is needed or maintenance. This is a filter. As you can see here, there is no pointer to an interface filter because the filter is generic, can be reused by any interface filter. And here we have the rules that are in this access list. So we have the action, the permit, the protocol, the left address and right address. You see this left and right goes back to the left and right domain. So we know this address belongs, and the port, other information. A rule, how it's built. The rule is linked to the filter. We have, and then they define the action that we'll do. So it can be a permit or deny. We can choose all the protocols. We have a relative sequence number inside this filter. It can be ACMP. And then we have the left and right addresses. This is in on the type of address can be different. So if a generic one is unknown, so we can write any kind of address. But then if we use one of the other network set service host, is something that is already defined in our database. So this is useful when we renumber the machines. So we don't have to worry to go back to the firewall configuration and change the rule, because if the machine is renumbered in the database, then the change is automatically applied in the firewall. And then here on the lower part, you see some information that are used by the security teams to know who requested the rule and the reason why it has been requested. Then we have this page that is a public page for the CERN users. The CERN user has, this was a screen that was already available with the information of the machine. Every user can see some information about his machine, where it's connected, for instance, and the name, the IP addresses. And then we added this box that is allowed to make a request. Clicking the button, we go in this page. you can see there are some already predefined requests, the most request one. So most users ask for opening the SSH port or the web port, but then also we have these ranges for the grid. Otherwise, they can, if nothing of these predefined requests are good, the users that knows what he's asking can put its own application. So defining the protocol and the port number. And then they have to give an explanation and have someone that support this request. The approval procedure, the users fill the request on the form on the web. An email is sent to the security team. They check, they do some scanning on the machine to see if it is all the upgrades are applied and if it is secure. So they can either deny the request or approve it. If it is approved, the rule is inserted in the network database using another page of the application. And then the software sends automatically to the firewall. The users can also check what is open for his machines. So they can, here, if they go to this network register page, they can check what is open, all the ports. This is an example. Another feature that we add is the use of set. So the source and destination address can be not only a network or an IP address, but can be a set of machines. It was here, if you remember the traffic rule screenshot. So we choose set, and then we define a set. And then there is another page that is accessible from the users, where the users can add a machine to this set. This is especially useful for the grid, where we have hundreds of machines that need, for instance, the same openings. And this machine can change, can be renumbered. So in this way, we offloaded the task of changing the rules from the security team to the end users, so they can have access to this management page. They can change their set. And then for this set, there is a well-defined opening. For instance, in this case is port 2811. So all this machine in this set will have this port open. Then there is a configuration manager software that this software runs every 15 minutes, and it extracts all the information from the database. It builds all the configuration and tries to optimize the access list. We'll tell you later, we have a problem with the size of the access list. We have already for more than 3,000 lines. And since we have this control of we can allow the users to enter a single IP address, this software tries to put together IP addresses that are adjacent and try to build a network from this, so to reduce the number of rules. It checks that everything is consistent. It means that another control that we do is that we don't download a configuration that has too many changes from the previous one. This is because we want to avoid that the problem in the database, maybe the database was not online, can cause the deletion of too many rules. Also, we do an estimation of the hardware resources that will be utilized by this access list. So we avoid to download an access list that can be too big for the device and can kill it. So if all the checks are passed and there are differences between the built configuration and the previous one, the one that is running, then it is downloaded. Otherwise, if they are the same, nothing happens. So some few experiences we had. As I said, we have we can have problem with the size of the access list. The software is based on a database with almost no limitations, so in theory we can build millions of rules, but the hardware is user real resources, so we cannot download everything. As you can see, these are the two firewalls and these are the two driving routers. We have already 3,000, almost 4,000 rules that occupy 5% of the memory in this case. And in this case, less rules use 11% of the resources. So the check I mentioned before is this one. So if the access lists are too big, we don't download them. Another problem we had, it's not clear how many resources a single ACL entry can use. So something is documented, something not. So we did some tests, and for instance, a rule like this, where we have a TCP range both in source and destination, if you use 30 lines of this, they will use all the resources available. The problem with using all the resources is then the access list will not be executed in hardware any longer, so they will go to the CPU and everything will be slowed down. The same problem, we have the policy-based routing. Some operators will decide what is the next stop, for instance, so are not executed in the line card hardwares, but they are sent to the root processor CPU. And this causes a lot of load on the machine. And so we had to change the design ongoing because we realized that some rules were not correctly executed. Regarding BGP, we could have had other options. We could have used external BGP between the internal and the internal network and the outside network, using, for instance, private S inside or BGP confederations. We would have saved a lot of peerings, and so the configuration would have been simpler between the inside and the outside, but it would have required too many changes in the external network. So since it's a live network with many peerings, we decided to not go this way. So conclusions. With this new system, we have a stateful firewall that can deal with the traffic load that we have today. Today we have almost 500 megabits per second, but we tested it up to 2 gigabit per second. And when this box, we couldn't buy the most expensive box, so we decided to buy what was enough for today and probably next year, and maybe hoping that maybe in 2 years, 3 years, the market will propose something better at an affordable price. The overall bandwidth of the system can already match the external connectivity, that is 20 gig, and can scale beyond 80 gig easily, just a matter of adding 10 gig interfaces to the box. The management framework can use all the information we have in the database that save us a lot of time when there are configuration changes, and can manage any gate. That means that we are using already for protecting other parts of the network. For instance, to protect the experiments, they have a dedicated network, so we put other firewalls in front of them just to avoid to have problem with these control machines. And also we have these automatic updates that automatically apply changes without any human intervention. So we are happy with the system that we built because now the management of the firewall is much simpler. Okay. Any questions?
Firewalling 80 gigabit is a challenge. Question up there.
Brian O'Hara at Trinity College Dublin. Could you give some indication, please, of the approximate cost to build and operate?
So can you say it again?
Could you tell us how much it cost to build and to operate? Euro, a value.
The cost of the system?
Yes.
The hardware. It was around 200,000 euros.
Thank you.
Just here. Sorry, I haven't been here from the beginning because you started early. Maybe you have answered it already. How do you differ between traffic flows? If you have a router, normally you route from source to destination.
Yes.
If you have if you have a large data flow and a small data flow, are they going the same direction? Or if there is a large data flow, is it going not going through the firewall, and also small data flows going the same direction, not going through the firewall? Should be foil 17.
17. This one. So this box do policy-based routing here. So it identifies the traffic based on source and destination IP addresses, and also, if possible, on the TCP or UDP port. So we do use policy routing to identify.
The routing. You can differ the routing also on the ports?
Yes.
Okay.
How many users you have in your system, which are under your control?
So the CERN community is 4,000 people. So the hosts are 10,000, I think.
10,000 computers?
Yeah, probably more. I don't have the correct number. Sorry.
And the loadage of your system, do you have any reserves, or it's on the border?
Sorry, can you say again?
So, about loadage of your system. So, do you have any reserves for? You have 4,000 computers, as I understand.
Yes.
Is it possible to add and have 40,000 without changing your hardware?
Yes. The system can scale. Well, the software.
Scalable,
software can scale. The hardware has some limitations. So if we can. We cannot apply any kind of access list to the current hardware. So what we tested is, I think, is 30,000 lines. Now we are 10%, let's say, of the capacity.
Thank you.
But we don't have a rule for every single host. We try as much as possible to use networks, but it's true that in some cases we have to go down to the single IP address or the TCP port.
I have two questions.
Yep.
You say you have 4,000 computers or 4,000 users. Do the when a user makes a request,
yes,
you're saying the security person checks it. So do the security people know what each of those users are doing, or do they just do some sanity check to make sure that the request is not stupid, or do they know what each person is allowed to do?
For the generic request, I show here this one, SSH web server. They have some scripts that do some scanning on the machine.
Okay, so it's not about what the individual is allowed to do because of the job that they're doing. It's just, is the rule sensible?
In principle, they should do something related to their job. So
okay.
We have some policies inside, but it's true, we don't check the content of a web server.
Okay, and the other question is, when a user requests a change, does the change stay forever, or are they time limited, so after a while they have to renew the request?
Yeah, here they can put an expiration date. It's not mandatory, so normally the rule stays forever. But if there is a demo or an experiment that the user knows that will end, so they are asked to put the expiration date.
So I just saw in the foil before you had grid FTP port 2811. Which other ports do you open for grid FTP? Do you open the 5,000 ports which are recommended from grid FTP, or grid FTP is using dynamic ports also? And,
I think it's this one range, this 20,000, 25,000, I think.
Yes, that's the part which is recommended for grid FTP also. So you have to open both.
Yes.
Okay.
Nothing else? Okay, let's think it well again. Bilbao. So these slides are going to be hot off the press, which also means that anybody watching with streaming, unfortunately, won't be able to see these slides or download the slides themselves. Shouldn't be necessary.
Yeah. Okay. I use this one. Yes, thank you, Chairman, and good morning, everybody. Yeah, it's my honor to join this TNC meeting first time for me from China and also from CAS. So I'm very enjoying this meeting, and I would like to exchange some our workers and experience in the last time and in the near future. So my topic is about future networking for the e-science in the CAS. Which one? Okay. So there are some topics I would like to show you. So this is the headquarters of Chinese Academy of Sciences, located in the center of the Beijing. And also, CAS is a very old research organization in China. It's founded in almost 50, 60 years old. And also, it had its academic institute in Natural Science Research of China. And also, yeah, that is in the almost 50 years ago. Yeah, more than 50 years ago, that is the old building headquarters in the Beijing. And another is the new buildings in Beijing. There's a total staff of CAS more than 45,000, so which of them 13,000 senior researchers, and also there are some 30,000 professional for workers. And also we have 30,000 visiting scholars, including postdoctor and the graduate students in the Chinese Academy of Sciences, distributed in all of the institute. And also there are 12 branches distributed all of the China, and 97 institutes, and also 2 graduate schools and University of Science and Technology of China. Of course, there are 9 supporting institutes in the CAS, including our CNIC, that means Computing Network Information Center, that is supporting technology system. So this is the distributive for the CAS in almost every province of China, including Xinjiang province, and also in the Tibet. So there are some new institutes located in these areas. So For the case, we focus on the natural science research and some high technologies. There's some field involved by the case, for example, in the basic research and life science and biotech, and some resource and environment, and some high-tech research and development. So there's some high-tech involved architecture achievement in recent years, different areas. I'm not familiar about this different aspect field. And you look like some things, so including some SaaS research and some other things in the case. So, and also some paper announced in the natural science and some things like that. So these are some big science projects recently year, hosted by Chinese Academy of Sciences, actually by different institutes. So that means, according to my introduction about the case briefly, so that is the question next. What kind of networking should to supporting all of these institutes and all of these research workers? So that means we used our CSTNet. CSTNet is China Science and Technology Network, and one is one of the distributed basic foundation for all the research of CAS in the past, current, and future. But I think currently CSTNet not just service for the CAS and outside provide services for outside of the CAS for different research and the government. So CSTNet have very long history compared with in the other network in the China. So founded, it's just 11 years ago, 13 years ago. It's the earliest internet in China, and want to provide nationwide advanced network infrastructure for all the scientists and the research institute of China, and also to provide some networking services for all of them. And so the history of, for the CSNet, there's some background for his founded. We can go back to the 1989, that NCFC project supported by the National Science Foundation, means by the World Bank. That is almost 20 years. And another CSNet, the former CSNet is the CASNet. This means almost, more than 14 years ago. So Chinese Academy of Sciences started his original network. So just want to connect all of the institute at that time of CAS. And there's a very important milestone in this CSNet, that is 1994. So under the supporting from the government, from the US, and from other partners of international partners, we set up the very important and first internet in China. So that is the current for our CSNet. I think we also provide some services for the networking and video conference and video and web email services for all of these institutes, and some CSNet center, and also we provide now the VoIP services for all of these institutes. So we call these services is just public and common services for all of these institutes. This is our environment and search for the CSTNet, and also email web based on the CSTNet, and also we use the CSTNet to set up a video conference. So this is very important in the 2003 year, because at that year there was some SARS in the China, so the most people couldn't travel from different cities So at that time, the headquarters of CAS asked CSKNet to set up the first video conference at that time. That's very useful for all of this research work and management for the, So I think currently there's another very important thing in the CSNet that we used CSNet to promote the international cooperation with different research organizations. So we call this Gloria project. It started in 2003, supported by the National Science Foundation of US and also Russia. Kurchatov Institute also involved in this project. Currently, we have more than 11 members in this in the Gloria meeting. So also, we set up a Hong Kong Open Exchange Point or Hong Kong Light to exchange the different, connecting and the different connections in the Hong Kong. And also, currently, we just to promote the Beijing Light buildings for some other, based on a national project, CNGI. So this is a situation for the CSNet. And also there's some Gloria and the Gloria CN's workday. This is the open ceremony in Beijing 4 years ago, 3 years ago. And also this is the great open ceremony in the Korea. That is our second big open, big Gloria ceremony. So this one is the meeting in the Hong Kong in October. I forgot, October 2005. There's a big, it's a very nice meeting, collected not only just the people from the Gloria and also from some other global networking. So Hong Kong Light is very important in our CSNet. So we can call Hong Kong Light is as expensive for our CSNet into the international. So we set up this, set up this Hong Kong Light in November 2004, and also there are some workers continues in this in Hong Kong Light. Currently, we upgraded our from Hong Kong to US to up 2.5 gigabits based on light path. Another very important for us is we are doing some things from Beijing to Hong Kong to optic link, also based on the light path. So we are just testing this link. So this things about Hong Kong Light. This link from Hong Kong, from Beijing, Hong Kong, and then to some of our partners of Gloria. We call this link, or we call this light path is a source light path, because from our side, this light path from Beijing to Hong Kong, and then from Hong Kong to Korea to Seattle of US, the Pacific Wave, and use the optical link provided by the Canaria to the Starlight, and from Starlight in the Chicago to the Amsterdam. So some things we have done and we have tested about that. So at here I would to see this part. We just used this part in the 2 cups of months to do some testing for the VIBI project. We got very good result. I just mentioned by the first president. So there are some changes for this Hong Kong open exchange point. So you can see in the before July of 25, we just GSP, that is rotary, and then we are very fortunately, we got supporting from the SurfNet, so installed some new things in here on ice. And also, recently we just installed some OME, the switches from the hotel. So there's some changes, and also this changes means that our CSNet not only just provide general services, and also we should provide some services, the advanced services for the big science project or big engineer project. So there's some Beijing light, because you know there are some big project recently years in China, that is China next generation internet supported by the government. So some budget have been put on this project, and some things we have done. One is the backbone based IPv6, total about 38 gigabytes. And also we will to do some IPv6 technology and applications based on this environment. And also the most national ISP project, ISP joined this project, including some, all of these commercial ISP joined this project. So that is the map for this backbone for CNGI. And also what things we will do in this project for the CAS and for the CST night. So we combined with the CNC company to set up 7 gig POP in the China, in Beijing, Shanghai, Guangzhou, Chengdu, Lanzhou, and some other cities. So, and here we would like to say some things for our workers of the CST night in this project. So firstly, we have to provide connecting the more than 100 science and technology network based on CST night. So that means one of the 40 networks should be involved in this project. So most of them, not only just for the CSNet, or most of them from the different areas and the different government. So most of them located in Beijing. That's why we can provide them interconnection very easy. So another thing is the CAS should be connecting the 60 institutes that in Beijing, Shanghai, Guangzhou, and Shenyang, and some other places to join this, including some national lab to join that. This part we want to provide some science application based on this environment. So the connecting bandwidth should be 1 gigabits to 10 gigabits, and also we should to CSNet to providing supporting technology to science application, and also some new technology have been put down. So there's the name list for all of this networking, and institute joined this project. So you can see some China Earthquake Data Center, and the China Meteorology Data Center, and some China Topography Science and Data Sharing Networking, and including some Chinese Academy of Social Science networking also involved in connecting in this project. So this is some website for all of these new members of China, including National Agriculture, Scientific Data Sharing Center, and some Geoscience Resource Center, and some other things. Yeah, okay, thanks. So that's why, based on this project, we have to set up our Beijing Light, also we call the Beijing Open Exchange Point. Even though it's 5 years ago, promote want to set up Beijing Open Exchange Point, but now we think this is a very good opportunity based on CNGI project. So we have optical fiber connecting with almost 20 national science and technology research workers that is covered many different science areas, not only just for CAS and outside, most of them outside CAS. And also there's an exchange center on the data, scientific data center in China, all located in our CAS, and also provide a platform for all of these corporations. So that is the Beijing Light recently processing in our CNIC. That is a structure for the Beijing Light. I can't, it should be look a little simple, but the next time we will step by step upgrade this center. So next, I would like to say some things about the future workers in our CST Light. So generally, I just mentioned that most of the workers have been done by CNET. By CSNet, it looks like skilled quality services for all of these users, the CST users. But currently, we have to face some new challenges from the CAS, from the national, from the CNGI project. So the one is the important patent is about the e-science project. It's just approved by the headquarters of Chinese Academy of Sciences last year. So for this e-science project, how provide services and how provide some different technology to supporting this e-science project. That is the biggest challenge for the CSNet. Another very important thing, currently we have enjoyed and involved with some big science application in the CAS. Also, some of them is international cooperation for some big science application. So how to provide some supporting and to fashion this different new requirement. That's also another kind of big change for the CAS. This is the CAS e-science framework is approved by the CAS Hall last year. So you can see there are several layers, 5 layers. So from our side, we often call this the CAS e-science hamburger. It looks like some very, so the 2 yellow layers look like some cheese. So actually, we use these 2 yellow layers to integrate some resources, including data resources and some resources of research equipment and some other databases and some other things. So for the virtual lab layers, we want to provide a unique platform for the research workers based on different projects. So you can see, yeah, the networks is very important. It's the fundamental for all of these platforms. So what things we can provide to supporting our e-science project in the next maybe 15 or 20 years old. That's a big challenge. So we want to construct an e-science research environment. So that is for the well-field investigation in the near future, we hope. So we use the high-speed network connecting some research investigating in the well field. So some scientists always go out to city to the well field, including in the Tibet or some Qinghai province. And also, we hope to provide some mobile research environment for all of this research work and connecting our digital simple museum and also digital library. And also we want to set up a coordination research environment. Now we are just promoted like this. Currently, there's a big project in CAS that is Fruza project, cooperation with the USTS partners. We have set up a premier environment for these workers. and some observation domain, something. This is for the in this institute research workers in the e-science environment. We hope to get the data resources from some places and transfer to our data center and some data storage. And also they can use the data based on the high-speed network to do the data simulation. And also they can set up their coordination workers with the ITARI, with the CERN, or even though with the VIBI international partners. So and here I want to show you some very big project in CAS. One is the International Cosmic Ray Process Center. This project is cooperation with the Italy Infant Institute. So about maybe 4 or 3 years ago, I forgot, maybe 4 years ago, so they will set up a cosmic ray in the Tibet. It's a Yangbajing, it's just close to the Tibet. So this is the first cooperation for the cosmic ray in that areas. So in this project, Argo project, there's more than 10,000 detectors installed in these blue rooms, and every year this raw data more than 300 terabytes, and the reconstructed data maybe 40 terabytes 1 year. So the Institute of High Energy used the computing to do this reconstructed data. So currently we have connected these cosmic ray stations from Tibet to Beijing and then to Italy. So that's very useful. So at the beginning, I know the research persons just collated all of this data from every day and then mail this data called to the Italian Infant Institute. But now they translate all of data real time to the Italy and to the Institute of High Energy Physics. This is the observer. Last year, this station is no more running now. So this is the environment inside of this observer. So what things we do from the CERN night? So at the earlier of the 25 year, we set up just 8 meg-based link from Tibet to Beijing. So next year, we upgraded this link into 155. So that's very useful for this data transfer. And also, in the Institute of High Energy Physics, they built a computing environment based at the CG project of CERN and the cooperation with CNIC and the Italy Infant Institute and cooperation with Euro-China Create project and the Euro FTC Frankfurt. So this is the currently for this project. The international connection, we use the Gloria. That means that every day we transfer data from the Tibet, past Beijing, and then to Hong Kong. From Hong Kong to Seattle, transfer the cross US to the Chicago, and then to Netland, to the Amsterdam SurfNet, and then to Italy. That is the road for. And the second project, just the former speaker mentioned, that LCG project. So this is a project also involved by Chinese Academy of Sciences. The Institute of High Energy joined this project, and the cooperation with the IN2P3 Institute in the French. Yeah, we have set up Tier 1 and Tier 2 connections based on CERN and Gloria. So that is some workers in the LCG too. You can find some the Beijing CNIC LCG too, and also there are some other works you can check. So the third big project is about Beijing electronic position collected by the High Energy Institute of KAIST. These workers, the second for this phase for these workers started in 1989, but now this project upgraded by the government. They want to set up a computing environment, so the CPU should be more than 1,000, and also storage should be more than 3 terabytes in these 5 years. And they need very high-speed network to international and domestic communication with other companies. So recently we just talked with the director of this institute. He told me he hope have two and our team back-based gate-based network and brought with our CNIC. So another big project is VLBI astronomy. I just mentioned by the first speaker today. So this is for the global VLBI project. But in China, there are currently four astronomy observatory have been involved with this project. So Shanghai Observatory is the leader for all of these groups. The one is in Shanghai, Sheshan, another is in Beijing, and another is located in the Xinjiang province, Nanshan Mountain, and another in the Kunming. So, from last year, since last year, there are some workers have been done by CST to provide networking for these for these observatories in KAIST. So currently all of these observatories have been linked by the CST and also as a very important port for the Shanghai Observatory have been linked with the Amsterdam, used the light path technology. So this is, I'm sorry. This is in Urumqi, Nanshan Mountains for this. And this is the pictures from the Shanghai Sheshan. And also we connected with the Japan, VIBI, some in the Kashima city. So this is just set up 2 years ago, and last year set up this networking from Xinjiang province to Beijing and then to Shanghai. We used 155 GB just for these telescopes. So that is some connection from the telescope to the Max 5 and the Max 5 to the router and then to our some other things, then to CST. All of the data will be collected, sent to the Shanghai Sheshan Observatory. So, according to some discussed above, so some futures, that means we have to face the different big science and engineer project. So, what is the future for features for this big science and big engineer? Because we have for the KAIST, for the CSNet, we have to face the challenge from this big e-science application or big engineer application. So one is the last mile networking for, okay. And another is the amount of data transfer and in time or real time. And for this transfer should be not interrupted and should be provided high qualities. And also this kind of data transfer usually, according to some studies by our CSNet engineer, so mostly of the burst data transfer just in some period, 1 day, not all days. So, and also this transfer generally across the multi-region, international, and different institute and some things. And the end user generally would like to control this data transfer and some things. So that's some things. So what technology solution should for this requirement from the big e-sense or engineer? Routing networking or other LightPath networking for us. So that is a big challenge, and we have to choose. So we do some things after 2 or 3 years. We got some testing result from the LightPath. One is the firstly, we tested the performance from the high energy physics test to the IN2P3 institute. So we do some things. First, we set up LightPath end to end, just means from Hong Kong Light and to the Night Light, the Amsterdam. We just used 625 bandwidth. That is a part of our 2.5 gigabit link. The second step, we tested the performance just from Hong Kong and Amsterdam LightPath. We got some results. Yeah, before we changed the MPU and the TCP, the performance is not so good, even though we provide enough bandwidth for this use, but not good. So after we changed the MPU and the TCP, we got very perfect performance. Just step 3, we added the end user at the end of this 2 gig part case, and the Institute of Energy Physics case, and the IN2P3 French. We used the router, but it seems not good performance. We used the LightPath one to do, but this work is no result. This is not for these technology issues, for some other issues. So this is the LightPath from Hong Kong to Chicago, and from Hong Kong, to the Amsterdam. So unfortunately, it's very lucky for us. From the Pacific Wave to the Chicago, the Canarian provide 2.5 gigabits connecting this link. So this is very useful for this project. And here I would like to say hello and thanks for all of the partners for the Gloria. And that is some test bed result by our engineers and some traffic monitoring by our engineers. So another test bed to the performance from Shanghai observation to the GIF Amsterdam just last month. So first test bed also we used the same LightPath. The second time, the performance we got from Hong Kong to Amsterdam, this performance perfected. And the third, we added the end user, GIVE and Shanghai observation used the router technology. Also, we got very good perfected. So I didn't put some result here because too long for this. So there's some result and some idea from our side. So broad bandwidth and the private channel necessary for this big sensor and the big engineer. And the IP protector and the router technology may be not very good enough for this requirement. And the LightPath may be one right choices for this kind of user application. But I think the bandwidth distributed should be dynamic, on demand, and regular. And also maybe TCP/IP protocol modified if we use the LightPath, and also some other things for the networking management and a lot of new technology issues have been occurred now. So that means if we want to use the LightPath, we have to do much more work on this, based on this technology. That's all for me. Thank you again.
Yeah, we we already passed our time window. I'm sorry, but there's so much thing going on in China that we had to get it over with this. I'll accept one or two questions if somebody's biting. Otherwise, get her in the break. Right?
Hi. Could you please explain what is the relation between the two Chinese research networks, CSTNet and CERNet?
Yeah. So always I was asking about these questions. Yeah, actually this network is supported by different organizations of China. So CERNet is supported by the Ministry of Education of China, and the CSTNet actually supported from the Chinese Academy of Sciences. And this means this organization supported. Another thing is we have to face the different application. So CERNet currently focus on the education for the student, for some professor to use that. For the CSTNet, currently we focus on the research workers. You can see. So that's why in the CNGI project, there are two part things for the application. One for the education publication, so will be should be doing by the CERNet. But for some research workers, I just mentioned more than 30 research workers connected with the CSTNet. That means this network should to provide good qualities and bandwidth to supporting the research workers. So but actually we have very good cooperation, you know. From this network, we have already connected each other in Beijing, and also we have a good, very technical cooperation between these two workers. And also we have very good personal relationship with, for example, Dr. Wu Jianping and some other persons. So that's all. The focus on the different areas.
Okay, thank you. So this was the last biggest session. We now have the plenary at the usual plenary place at 11 o'clock. So we're taking your time. Please get there in time. And remember that the buses that leave at the plenary place and not from here. Okay? Thank you. And let's thank all the speakers again. Sorry.
Thank you.